Okay, we will go through the exemplar problems in class 12 physics chapter 6 electromagnetic induction. Okay. So I will show you some basic things. Integral of dx by x equal to ln of x, that is natural logarithm of x. Okay, and the change in distance by time dx by dt is velocity. Similarly, change in velocity over time is acceleration dv by dt. So this acceleration can also be expressed in terms of the distance like this, d square by x by dt square. When you do cross product of I cross j, that is the resultant will be k, but if you do ulta j cross I equal minus k. Okay, and j cross k is I, k cross j is minus I, k cross I is j, I cross k is minus j. Okay, the current is rate of change of the charge. Okay, this is also expressed in terms of EMF divided by the resistance. The magnetic flux is NBA cos theta. N is the number of turns of the coil. Okay, when N equal to 1, it will become BA cos theta. This is force on a current carrying conductor BAL sin theta. This is a mutual inductance. Of two coils, if we take M1 and M2, mutual inductions of 2 with respect to 1, mutual inductance of 1 with respect to 2, both will be same. The mutual inductance is equal to the magnetic flux, the current on the other coil. Okay, the magnetic flux on the coil divided by the current on the other coil. Okay, this is the EMF, rate of change of the magnetic flux over the time. This is for the N terms. Angular velocity equal to 2 pi into linear velocity. Linear velocity, angular velocity, motional EMF BLV. L is the length of the conductor, B is the magnetic field, and V is the velocity. Okay, EMF also can be worked on by unit charge. Okay, rate of change of the flow of the charge, rate of change of the flux over the resistance of the conductor. Okay, change in the magnetic flux. Okay, this is change in current or the charge, you can say. N pi by equal to Li, where L is the self inductance, I is the current, this is the magnetic flux. Okay, this is self induced EMF or back EMF, that is equal to the inductance divided by rate of change of the current. So if you substitute N equal to NL, pi is B into A. Okay, BA. B is mu naught Ni, A area, then NL cancel, and this equation you will get. This is the magnetic potential energy equation. See, in a magnetic field, when there is a closed loop, current carrying conductor is moving away from the field. This is the direction of the current. So when you move away, the flux will decrease, but the induced will increase to keep the flux constant as per the Lenz's law. Okay, but here it is coming into the field, so the magnetic flux will increase, so induced will decrease to make the balance. Induced oppose the change in the magnetic flux. These two current carrying conductor, one current going this way, other is current going, this is the field. Here going inside and coming out, here this going inside, coming out. So it is in the same direction, so going inside, coming out, this is going inside, coming out. See, field here you see. A square of side L meter lies on the plane xy plane where the magnetic field B B naught is constant. Okay, the magnitude of the flux passing through the flux is PA cos theta. Okay, so the area vector is perpendicular to the plane. Here perpendicular to xy means it is in the z plane, that is K. So one. So this is the magnetic flux equal to B dot A. Okay, so the area vector is perpendicular to xy. Okay, that is the K. So this is the B naught. So here dot this A B dot A. So when you do cross product, okay, only K will be multiplied. There is no I component and J component in the area. Okay, so only the K component multiplied, and this is the 4B naught L square Weber. That is the unit of the magnetic flux. Okay, so this is on a loop made up of the straight edges. Okay, these are the coordinates. Magnetic field is present in the region. The flux passing through the loop. This loop is again the same formula we have to use. Here only the area computation we have to take care. So these are the coordinates they are given. Okay, this is the area. So area is this much. Okay, this L square. This I K. B dot A. B is given. Okay, then B dot A. So here the important thing is that when you have the components, how you multiply these vectors, that is the important. Okay, the B. Here there is one I component, there is no K component here. Here no I component, only K component here. Okay, B naught L square plus 2B naught L square. A cylindrical bar magnet rotated about its axis. Okay, rotated about its axis. A wire is connected from the axis and is made to touch on the cylindrical surface. Then the direct current flows in the ammeter is connected here. It is rotating. The flux won't change. Okay, it is rotating in the vertical axis. No flux will change. No current flows through the ammeter because there is no change in the magnetic flux. This is the direction of the rotation. Okay, the flux will change only if you rotate move in this direction. There are two coils A, B. Okay, the current start flowing B as shown when A moves towards. Okay, that is important. Only when A moves, the B has the current. No current in B when A stops moving, and stops when A stops moving. The current in A is counterclockwise. It is kept stationary when A moves. We infer that, okay, there is a constant current in the counterclockwise direction. See, whenever this comes close, the magnetic flux will increase. The induced flux will oppose. So the direction of the current will be such that the induced flux oppose the original flux. Same as the problem 4, except that A is made to rotate about its vertical axis. No current flows when B and A is red. The current is when the current V is 0. Okay, so here it is rotating. The flux is changing. Okay, it is not coming closer. So that is a constant current. in the clockwise direction. The self-inductance L of the solenoid of length A, area of cross section A, the fixed number of terms, and so you have to know the formula here. Okay. This is the self-inductance, that is, this formula is taken from the book equation 6.17. So here you substitute for the n, this is the turns per unit length, the total number of turns by the length of the length of the solenoid. Okay, so when you substitute this, so this L will cancel, then it will become, formula will become like this. So now they are asking, the L decrease, in L decrease, so the self inductance L, here L is in the denominator. Okay, the length is in denominator. When L is decreases, this will increase. Similarly, when A increases also, this will increase. A is directly proportional, and this length of the solenoid is inversely proportional to this self inductance. That is what L decreases, A increases. 20. Okay, that is given here. This formula. A metal plate is getting heated. It can be because a direct current is passing through the plate. It is placed in the time varying magnetic field. This is not correct. This is space varying magnetic field. That is not correct. This current in either direction is passing through the plate. Okay, one, this D, A, B, D, these three are the correct ones. So this space varying is not correct. And EMF is produced in the coil which is not connected to the external voltage source. This can be due to the coil being in a time varying magnetic field. Okay, the coil moving time varying magnetic field, moving in a time varying magnetic field varies, that is important. The coil moving in a this coil is moving, but the magnetic field is constant. Okay, because coil is moving. So this does not change with the time. This is incorrect, not changing with the time. Okay, 5. Okay, this is changing with the time. Okay, then only this flux will changing with the time. See here, changing with the time. Mutual inductance of coil M1 to coil of 1 with respect to 2 increases when they are brought together to nearer. Okay, that is mutual induction will increase when they are closer, is same as the M21. Okay, mutual induction of two coils are same as I already showed you. See here, mutual inductance of 1 with respect to 2, both will be same. A circular coil expands radially in the region of the magnetic field and expands, but there is no electromotive force produced in the coil. Okay, this can be because the magnetic field is in the same plane as the circular coil. Okay, the angle between them will be 0. Angle between magnetic field is in the same plane as the circular coil and may not vary. Okay, there is no variation in the magnetic field. Okay, variation in the magnetic field. The magnetic field is a perpendicular to the plane of the coil. Okay, magnetic field perpendicular means cos 90 will become 0. Okay, ba cos theta. So flux is ba cos theta. When cos theta is 90, cos 90 is 0, so that means there is no EMF will be induced. Very short answer. Consider a magnet surrounded by the wire. Okay, this is the magnet surrounded by the wire with an on-off switch. If the switch is thrown from the off position to the on position, will the current flow in the circuit? No, there won't be any current flow because the magnetic flux won't change. No movement here in all are stationary. Okay, 11. No part of the wire is moving. Okay, so the motional EMF is 0. The magnet is stationary and hence the magnetic flux does not change. This means that electromotive force is no electromotive force will be produced and hence no current. A wire in the form of the tightly wound solenoid is connected to a DC source. Okay, the solenoid is connected to a DC source and carries the current. If the coil is stretched so that there are gaps between the successive elements of this coil, will the current increase or decrease? This is based on the Lenz's law 6.12. The current will increase as the wires are forced apart. The flux will leak through these gaps. Okay, they are stretched. The flux will leak through between the gaps. Okay, so the Lenz's law demands that induced EMF then decrease. Okay, which can be done by increasing the current. Okay. This way, actually, as per the Lenz's law, the change in flux is resisted. Okay, when flux leaks through the gaps, this will be resisted by increasing current to increase the magnetic flux. A solenoid is connected to a battery so that steady current flows through it. If the iron core is inserted into the solenoid, will the current increase or decrease? Explain. 6.13. The current will decrease. As the iron core inserted into the solenoid, the magnetic field increases. Okay, and that the flux increases. But Lenz's law, it will maintain the steady things. Okay, Lenz's law implies the induced EMF should resist this change. Okay, this increase, which can be achieved by decreasing the current. Okay, so the main thing is Lenz's law will resist the change in the magnetic field. Consider the metal ring kept on the top of the fixed solenoid. Okay, say on the cardboard shown here, this one. If the center of the ring collides with the axis of the solenoid, the current is suddenly switched on. The metal ring jumps up. When it is switched on, there will be magnetic field formed at the center of the solenoid. Okay, the magnetic field will be strong at the center of the solenoid. Okay, no flux. No flux is passing through the metal ring initially. When the current is switched on, the flux passes through the ring. Okay, that is solenoid. The central magnetic field will be strong. According to the Lenz's law, this increase will be resisted, and this can happen as the rings moves away from the solenoid. Okay, ring is move away from the solenoid. One can analyze this more detail. Okay, in figure 6.1, if the current in the solenoid has shown the flux increases with the cause of the counterclockwise current seen from the top of the ring, as the flow of current is in the opposite direction to the solenoid. This will repel each other and link will move upward. Ring will move upward. So it will move upward because of this field. Consider the metal ring kept supported in the cupboard on top of the fixed solenoid current. The same thing. The center of the ring coincides with the axis of the. If the current in the solenoid now it is switched off. Okay, they are switching off the current. Here switched on, here switched off. Okay, here switched on, here switched off. What will happen to the ring? 6 dot. When the current in the solenoid decreases, a current flow in the same direction in the metal ring as in the solenoid. Okay, then there will be a downward force. This means the ring will remain on the cupboard. The upward direction of the cupboard on the ring will increase. Okay, upward reaction. Consider the metallic pipe with the inner radius of the 1 centimeter. If the cylindrical bar magnet of radius is dropped through the pipe, so okay, it takes more time to come down. Similar unmagnetized cylindrical iron are dropped through the metallic pipe. I think this is due to the eddy current that it resists the motion, so it takes more time. 6.16. For a magnet, the eddy currents are produced in the metallic pipe. When you drop the magnet in the metallic pipe, the eddy currents are produced in the metallic pipe. These currents will oppose the motion of the magnet. Okay, these currents will oppose the motion of the magnet. Therefore, the magnetic downwards acceleration will be less than the acceleration due to gravity g. Okay, if on the other hand, an unmagnetized iron bar will not produce eddy current. Okay, only the magnet produces eddy current on the metallic pipe. Unmagnetized iron bar will not produce eddy current on the metallic pipe, and this will fall with the acceleration, same acceleration as the gravity. Thus the magnet will take the more time. Okay, due to the eddy current resistance of this eddy current, it takes more time. A magnetic field in a certain region B is given with this vector K, it is K, and the coil of radius A with the resistance R is placed in the XY plane with the center, okay, shown here like this. Okay, find the magnetic direction of the current at this point, at these times. Okay, okay, 6.17. Okay, phi equal to BA cos theta. This is induced EMF. We have to find the current. First we have to find the EMF d phi by dt. Okay, B A is pi a square. Okay, that is the A is the radius. So the pi distance from the center, pi a square. So when you differentiate this, it will become sine d phi dt. Okay, BA cos theta, BA cos theta. This is the pi and d phi by dt. So cos omega t will become sin omega t, and this differentiate the time, then you will get omega here. Okay, now we have to substitute for this time t. I equal to EMF by resistance, okay, divided by R. Then at a substitute for T equal to pi by 2 omega. If we put pi by 2 omega, this pi will cancel out, omega will cancel out, sorry, pi won't cancel out, omega will cancel out, and then sine pi by 2. So you will get this for this time you will get the current this, okay. When it is at t equal to 5, then current will be 0 because sin phi is 0. T equal to this 3 pi by 2, then current will be like this, okay. Consider the closed loop. See magnetic field, this figure. The flux passing through the loop is defined by choosing the surface edge coincide with the loop using the formula. Because this variable area magnetic field, you have to add these things, okay. Magnetic flux are the different area elements you are adding. Now if you choose two different surfaces, these two surfaces having C as the common edge, okay, would we get the same answer for the flux? Justify. Okay, magnetic field lines form the closed loop, okay. These lines will pass through, same lines will pass through the surface, okay. It cannot end and start in this space, magnetic field lines. One gets the same answer for the flux. Flux can be thought of as the number of magnetic field lines passing through the surface, okay. As the lines of V cannot end or start in space, they form the closed loop. The number of lines passing through the both the surface will be same, okay. The flux will be same. Now find the current in the configuration, okay. This wire PQ is a negligible resistance, that the magnetic field coming out of the paper is a fixed angle, okay. This PQ, this is the thing traveling smoothly over the two conducting parallel wires. These are conducting wires and this is moving, separated by the distance D, okay. This distance is D. Okay. Electric field due to uniform due to the motion along CD, okay. This equal to VB sin theta, that is the cross product, okay. VB sin theta, velocity, magnetic field, and theta between, this is moving this side, angle between V and B. See, if you take using Pythagoras theorem, this sin theta equal to d by this hypotenuse. That is, the hypotenuse nothing but the length of the PQ, and this is d, okay. So that is what sin theta equal to d phi, the length of this. VB sin theta in the length of that. So that is VVD. This is EMF. This divided by resistance will give the current. This is the current, okay. Find the current. So answer. Okay, this is the current. current versus time graph of the current passing through a solenoid is shown here. This is the current time versus the current. Okay, for which time the back EMF, that is self-induced EMF, is maximum. If the back EMF at 3 seconds, 0 here somewhere here is E, find the back EMF at these seconds. Okay, maximum rate of change of the current is in AB. Okay, from here is the rate of change of current is maximum here in these curves. Okay, so the rate of change of current is in this 5 to 10, that is here x-axis 5 seconds, y-axis 3, 1 2, here this side 2, 1 2 3, here 5. So the maximum back EMF rate of change maximum in the AB, so maximum between these 5 seconds to 10 seconds. So EMF equal to L into di by dt. Okay, L into di by dt. D at 3 seconds, di by dt is 1 by 5. 3 seconds is somewhere here. Rate of change of current is 1, time is 5. Okay, 1 by 5 di by dt, 1 by 5 L. So at 3 seconds is somewhere, so this rate of change is constant from 0 to 5. Everywhere it will be 1 by 5 rate of change of the current. Okay, this is L by 5. So L into di by dt. Okay, L is constant, that is self inductance. For 5 seconds to 10 seconds, 5 taken, this L rate of change of current is 3 by 5. 5 to 10 seconds, this di 3, dt is 5, so 3 by 5. 3 by 5, okay, minus here t equal to 7 seconds. 7 seconds will falls within this, so it is the same. For between 10 and 30 seconds, 10 to 30 seconds, di is 2, dt is 20. Okay, 10 to 30 seconds, that is 20 seconds. Here 0 to 2, so 2 di, rate of change of current is 2, time is 20, 2 by 20. Okay, so now this is the change is 0. There are two coils A and B separated by the same distance. Okay, separated by the same, if the current 2A flows through the coil 1, the magnetic flux, the current. Okay, here you have to remember the mutual inductance will be same for the M12 equal to M21 equal to M. Okay, two coils. Okay, the mutual inductance will be same, AB equal to BA equal to M. Okay, the magnetic mutual inductance equal to the magnetic flux divided by the current in the other coil. So if you consider this magnetic flux at B but current in this coil. Okay, same way you can flux equal to the mutual inductance in the current. Okay, mutual inductance we found out this, then mutual inductance in the current is equal to the magnetic flux. Okay, here magnetic flux is given. The K vector covers a large region where the wire AB, this is sliding. Okay, the wires are in the XY plane. the wire AB of length D. This length is D as a resistance R, and parallel wires have the negligible resistance. This negligible resistance. A B is moving with the velocity V. What is the current in this circuit? They are asking the current. What is the force needed to keep the wire moving at the constant velocity? 22. B is given B0 sin omega t. EMF across B is work done by unit charge, work done by the AB by Q. This formula, work done equal to force into distance. Force Q, we see force, distance Q will cancel out. So the V, then B is given into D. Okay. On the B sign, then this I vector and K vector, cross product of I and K is minus J. Okay, I already shown you I cross J, K equal to minus J. So this will be, so we found the EMF. Now the current will be EMF by R, d phi by dt. Okay, this is phi dt. So along K. Okay, this one EMF. So there is a motional EMF and that other EMF. I equal to EMF by R. EMF by R divided by R. Okay, force equal to BID. This is force on a current carrying conductor in a magnetic field. So the vacating this. This is for the I. This portion we are substituting here. B, then I, then D. Okay, now for the B we have to substitute this. So after substitution you will get this answer. Okay, they given here the answer. Here conducting wire of the negligible resistance symmetry and tool. Okay, these things you can see, these all answers are given. 6.23. Okay, flux B into the area. This is the area. Okay, then BAL formula. Mass into acceleration equal to force. From that acceleration, then you divide this by mass, you will get the acceleration. Okay, the ODBAC is a fixed rectangular conductor of the negligible resistance. CD is not connected, and OB is the conductance which is okay. This also you can see for 6.24. So you can go through these answers. Okay. Consider the infinitely long current carrying. This is the carrying current. With the rate of change of current is the lambda as a constant. Find the current produced in the rectangular loop. In this loop, due to this current carrying conductor. Okay, the magnetic field due to this current carrying conductor at this point is mu naught L by 2 pi. Okay, the flux, magnetic flux at here is B into A. This is B, and A is the integral of x0 to x and this dr. Okay, now the dr by r is the log. As I will show, the integration of dx by x is the log x, that is natural logarithm of x. So same way here they are converting this integration into the log. Okay, E equal to d phi dt equal to voltage IR. Then from that they are finding that is this flux. Di by dt is lambda they are given. Okay, so the current, we have to find the current. So this is the current. Okay, see, for the other things, everything the answers are given. Okay, EMF by 4 is the current is the voltage by R. So you can go through the answers. Okay, self-induced plus motional EMF in this. So you can go through the answer, try yourself.